number, various Prandtl number here, and then if a larger here only from 0 to 7, approximately at 6, eta is 6, again it becomes 0. Okay, so that's the thickness of the boundary layer. When this becomes 6, that's the thickness of the boundary layer approximately. So various cases, for example, for Prandtl number 1, that's when it becomes almost. So for until up to 1000 to 72 you can do it, but very low Prandtl number, it can go large distances. So it's been plotted separately here up to 24. It comes almost like eta is 22. So the boundary layer is a very small. Prandtl number means the thermal boundary layer is very large. That's what it tells me. And similarly, temperature boundary layer can also be plotted here after solving it. And here again, it looks similar to the velocity boundary layer equations. Okay, so anyway, from here we can solve all the uh, the correlations of uh, the heat transfer coefficient and so on. So Nusselt's number is defined as, and here you will find out that dt has been given in terms of the Grashof number 1/4 power. Okay, because that's a t star, and dt over d star, because remember this is how we converted that dt was. So we need only the first term. So if you put the substitute all this, Grashof number becomes minus, I'm sorry, the Nusselt's number becomes as a function of Grashof number, and then the dt, whatever the non-dimensional parameter t star, if you get the curve, take the derivative at a slope at eta is 0, and this becomes Grashof number to the power of 1/4 and some sort of arbitrary function of the Prandtl number, and the Prandtl, this has been given as this for any large Prandtl number 0 to all the way to infinity. It's not a problem. So this is the exactly the correlation for Nusselt's number exactly solved. And then we know the Grashof number is in terms of the x distance along the plate is given as x cubed over nu square, and then the average heat transfer coefficient is given as 1 over L 0 to L of H. So H is given here, and then if you integrate that, if you Nusselt's number based on the total length, average Nusselt's number or the length of the plate is given as 1/3, 4/3 of the ordinary Nusselt's number. Okay, so of the length. So it's basically that is what it is. Okay, all right. So practically, we can also solve this using the integral method. If you look at the equation here, u infinity is 0. So let's just go back. Let me look at the what did we do for the uh, okay. So in the case of the forced convection, okay, so forced convection, the momentum equation converted to d over dx 0 to delta u infinity minus u dy is equal to nu du dy at y is equal to 0. Okay, so here only thing is in our equation here, this same u naught is 0. You don't have any infinity at all. So here, so what was our momentum equation earlier was the right hand side was tau, and then there was a term here g beta t infinity minus t was there on the left hand side, extra force. So that can be taken outside. So this becomes d over dx. There's a negative here which is taken to the right hand side. 0 to delta rho u square is minus tau delta. This is nothing but mu d square u dy over. Okay, plus 0 to delta rho b t minus t infinity. So I can integrate. This is nothing but mu. The rho can be taken out, so you can bring the rho here. That this becomes mu du dy. So that's my shear stress. So the nu earlier it was like basically nu. When I divide by rho, it becomes the kinematic is because nu and rho goes right here. So anyway, similarly, we can also convert this um, t minus t infinity also the similar way. So the only thing is the momentum equation will have t minus t infinity. So the way you approximate the velocity and the temperature profile is like this. If I see, look at the boundary condition here. So u is 0, that we know at y is 0, and u is 0 at y is also delta. There's no infinite velocity at all, and du over dy, it gradually, in other words, if I have the profile here, it goes maximum and gradually joins. So this is my delta. And because remember, we were having u du dy v du, I'm sorry, du dx, du dy was nu d square u over dy square. So at the boundary plate, u is 0, v is 0. So, and there was another term here. Remember, the other term was gb t minus t infinity was there. So that can be taken out. So you will find that d square u is equal to gb. This is all gone. I mean, was it new here? Yeah, okay. So the rho gets cancelled. Let's see. So it'll be, so that term was GB, isn't it? So minus GB. So it has to be divided by nu. That's right. So basically minus G beta T wall minus T infinity divided by nu at y is equal. So the nu comes in here. So there is one more term here on the for the natural convection. So there is one more boundary condition here. So this has to be satisfied. Okay, so if I assume all right, so basically I can assume if I assume a polynomial the way that I have done here, and the ux is an arbitrary, I just want to make this non-dimensional, so I'm dividing by ux, and you will find out that this, if I apply into this boundary condition, all the boundary condition, and apply that, I'll find out that there is this is exactly describes this kind of a behavior. So look at this. So this is 0. So you'll find there's a maximum occurs if I take the derivative with respect to y. The maximum occurs y is delta over 2 here. Okay, you find that. So, and dy dt also goes to 0. naturally at y is equal to delta, and then d square. So only thing is the ux. The ux is, you can define the ux. Here, look at this ux. So if I define the ux to be equal to beta del square g tw minus t infinity divided by nu is ux, then this all can be taken into ux. So u over ux becomes y over delta 1 minus y over delta square. So ux is a fictitious, but we related ux to a actual parameters of the problem. We are able to do that. It will be like a velocity, obviously. Okay, now similarly the temperature T minus T infinity over Tw over T infinity. So this will satisfy. So what is the boundary condition on temperature? At x y is equal to 0, y is equal to 0, this should be 1, which is correct. I'm sorry, yeah. And then at y is equal to delta, this has to go to 0, which is correct. T is T infinity. And dt over dy, see this does not, the temperature doesn't have, the temperature equation is u dt dx v dt dy is alpha t square tt over dy square. So at t is equal to 0, at y is equal to 0, d square t over dy square has to go to 0, which will be you will find out that will be true at y is equal to 0. Okay, so not a problem. So that is the reason that it just gives you the square of that 1 minus y over delta square. So it will satisfy all the boundary condition. Okay. All right. So now we can supply this into the momentum and general energy equation and solve approximately. But I don't think I've done it here. Let me see what I have done. I think it will be the same exercise as before. Let's see what. Okay. So I have done this. So if I integrate this, just the velocity profile, I'll find the buoyancy force is coming on that term coming to the right, and then this is the negative coming out of the ux. Remember, ux is a function of x, but that is a arbitrary variable, but we can relate that. And energy equation, so this is the integration after integration. So this is the velocity profile, and this is the integration of the momentum equation. Similarly, the energy equation becomes like this, because remember we have to substitute this. That is why this term comes in. So my ux, if I look at my ux, is approximately is proportional to the boundary layer square, the velocity x is. You can see the way that we have assumed ux. If you look at the ux there on the earlier page, so the ux was like a del square. So this is the ux. It's approximately proportional to del square. And similarly, the del itself is x to the power of 1/4. Remember the Grashof number 1/4. Okay, so that is why delta is proportional. So I'm going to assume ux is some sort of a constant. Since delta is x half, double of that will be half. So x of half, and delta will be c2x to the power of 4. So I want to substitute this into this and solve for c1 and c2. That is, see, I got to solve this differential equation, isn't it? So that's what I'm doing. So I'm substituting ux and delta here on the first equation, and similarly on the second equation. Finally, so this is kind of, I'm going to a little bit fast. So the constant c1 is given like this. This is a Grashof. It's not a Grashof number. This is like a non-dimensional number. So this is nu square is L square over t square. So this is L square. Okay, so beta over t. So this becomes, this has to be, oh, I see. It has to be equal to nu. Remember C1 x half is velocity. Okay, so C1 cannot be non-dimensional. Okay, so that's okay. So anyway, C1 and C2 can be determined. So delta x is, remember delta x was a Reynolds number 1 over Reynolds number square root. Here instead Grashof number 1 over Grashof number of fourth root. These are all some Prandtl number, some number here. But the interesting thing is, instead of Reynolds number 1 over square root of Reynolds number becomes 1 over Grashof number based on x 1/4 power. Okay, so I can solve for the heat transfer coefficient, and Nusselt's number becomes Grashof number 1/4 instead of square root of Reynolds number. All these constants all come out of this analysis here, and it's exactly similar. It's slightly different, but natural convection is main driver is the Grashof number. But since Grashof number and Prandtl number is appearing close by, looks like the product of the Grashof number and Grashof number and then the Prandtl number may be also taken. So that is what experimentalists have done. So empirically, a lot of empirical relationship for natural convection. So there was one number defined as Rayleigh number is multiplication of Grashof number multiplied by Prandtl number. Okay, so this Chu and Churchill for a vertical plate, the Nusselt's number is some constant number 0.68 plus this is the Rayleigh number to the power of 1/4. So the Prandtl number and Grashof's number comes in here, and then 0.67 comes in. There is a denominator based on the Prandtl number. It's kind of complicated. This is applicable all the way. 10 to the power of 9 is when it becomes turbulent. It's been established. When the Rayleigh number reaches 10 to the power of 9, that is when it reaches, it becomes turbulent. The flow becomes turbulent. It can become turbulent. And for anything in the turbulent region, so this is this particular thing for laminar flow in the boundary layer, and this correlation applicable for vertical plate for a turbulent flow. So anywhere from, even this is applicable for wider range here, 0.10 to 10 to the power of 12. So it's still applicable for turbulent. Now, for a horizontal cylinder, for example, you can relate that based on the diameter of the horizontal cylinder. The Nusselt's number is hd over k, where h being the average heat transfer coefficient is given as a function of c and the Rayleigh number to the power of n. This Rayleigh number is based on the diameter d of the cylinder, exponent n. And so for various Rayleigh number, this correlation works. So anywhere from 0.10 to the power of minus 10 to 10 to the power of minus 2, 675, it's almost close to this. And Rayleigh number to the power of 0.058, so 06, very close by. Similarly for various, so this here is a turbulent regime here, because 0.125 is almost like a 1/3, the Rayleigh number 1/3 here almost. So anyway, this is the practical correlation numbers. So some people have plotted this for vertical cylinder and vertical plate for two different 9-inch plate and about 3-inch plate for a vertical cylinder. Okay, so all the data, the circular dark data is for vertical cylinder. So that agrees with about 0.029 with the Prandtl, the Rayleigh number to the power of 2/5. So 0.4. So in the turbulent region. So let's look at the turbulent region. What did we find? Turbulent region is 0.4. Yeah, exactly. So looks like it makes sense. Yeah, Rayleigh number 0.25. Okay, and then here at the laminar region, it's 0.55 or 0.56, 1/4 also here again. So that's a exponent of 0.4, here 1/4. Whereas there, laminar is 1/4, that's right. But turbulent is 1/6, this is. Okay, so it's slightly off the 0.4. So, but anyway, this is a experimental result. So you can use either of this also. So the important thing is the non-dimensional parameter is the Grashof number and the Prandtl number. So depending upon the fluid, if you have air or water, vapor or oil, whatever, so you can work out your problem based on these correlations. Whatever is meaningful, that can be used. Okay. All right, let's just for illustrating all the technique, let's just do a simple problem. Very straightforward. There's nothing fancy about this. I'm going to consider a plate about the length of 0.25, and I don't know whether I assumed anything for the width. Maybe I did not. Okay, it's okay. And this plate is heated and is kept at 70 degrees centigrade. So its surface temperature is 70 degree. The plate is suspended in a quiescent air that is 25 degrees. So the surrounding air is 25. So the important thing is the property of the air has to be taken at the mean of what is called bulk temperature. So 70 plus 25, 95 divided by 2. So 7.5 degree, which is 320.5 degree Kelvin. That is my film temperature. And at that temperature, the kinematic viscosity, you look at any handbook or your textbook, it's about 18 10 to the power minus 6 meters square over second, about 0.7. This doesn't change for air. And then since it's I can assume an ideal gas, the compressibility or the volume coefficient is 1 over TF, so 1 over 320.5 is about 3.12 E 10 to the power minus 3, 1 over Kelvin. Okay, so beta is known. So the Grashof number based on the length is G beta. Ts is 70 degree, T infinity is 25, so for 45, and L cubed is 0.25. So everything is you can plug in everything, and then obviously the Grashof number is 6.7. So this is still laminar. So the Rayleigh number, I multiply this Grashof number multiply by Prandtl, so 0.7, I get 4.68 10 to the power of 7. So this is a laminar flow. So from the actual curve that I can solve, so 6L is a delta L, and this divided by the Grashof 4 to the power of 1/4. Remember eta, was 6L over delta L. So I multiply the length, and the Grashof number is we know divided by 4, so it's 0.024. My boundary layer thickness at the end of the plate will be 0.24, like 24 meters. I'm sorry, 24 millimeters. The velocity at that end, again, I can go back to that curve that I showed you. It's about 0.33 meters. It's very, very low, extremely low. So I plugged in the 2 eta and then F prime. So let's go back and look at the curve here. So Grashof number has been calculated. So F prime is about 6, is like 0.28. So it's 0.7. So at 6, so F prime theta at the maximum velocity is around here. So 0.28. So F prime is 0.28. So that is the reason we took that 0.28 was f prime, and Prandtl number and eta is 0.6. So I substituted everything here and then calculated that the maximum velocity is like 0.3 meter per second. It's very low. And then what is the equivalent Reynolds number? So the maximum velocity is I don't know. For airflow, that's okay. I'm not worried about that. So this is the equivalent. What is the equivalent Reynolds number? Is the Reynolds number REL square? No, that's also, I'm not worried about that. So if I have the conventional forced convection, if a velocity of 5 meters per second is given, what I'm asking, what exactly is the Reynolds number? Reynolds number for this plate would be about 7 10 to the power of 4. And what is the ratio of the Greshoff's number to the equivalent Reynolds number? That's how, what is the Greshoff number? Is basically buoyancy force divided by the viscous force. Hello? Here, Greshoff's number is very low, so obviously, the buoyancy force is very low. So the equivalent boundary layer thickness is only about 5 mil. Boundary layer thickness for the natural convection was 24 mil, whereas if it is a forced convection, it's only about 5 mils. So free convection boundary layer is for smaller velocities. It has a thicker boundary layer, so that is the reason the heat transfer is lower in natural boundary layer. I mean natural convections, which we know already, whereas forced convection heat transfer will be much higher. But the boundary layer thickness will be thicker in a natural convection. Understand? Any question on this? Any question? Okay, we can. Let's see what else I have. Do you have any question on those? Any questions on those three? The test, the quiz 6 at all? Anybody? Everybody is clear all the three problems? Anyone? Including the okay, I think let's see. The third problem, let's see, what was the third problem? Oh yeah, that's just a one. Okay, so you just solved. So the most important thing is, if I am using those kind of problem, if I'm using the approximate solution technique, this is all forced convection again. Well, we can do it for natural convection, but it's a little cumbersome. But let me just quickly touch upon that. So this is nothing but and similarly, this is all forced convection, okay? Okay, d over dx. Here, t infinity of u. Now, I don't have to go delta, because if my boundary layer, this is delta t, this is delta. So this is the momentum boundary layer or velocity boundary layer. This is the thermal boundary layer. Then I don't have to integrate. I want to integrate only up to delta t. So then again, this becomes okay. So the important thing is, you will find out if I take a complicated one, you will have to solve a boundary condition will involve a variable delta t over delta. If delta t is less than delta, then it will be involved that one, because this integral will give in terms of delta t, and then u will be in terms of delta. So you'll have a mixed value like this. They are all functions of x. Okay. So you'll find a variable. I have to introduce a new variable there to really solve for the Nusselt number. All right. So anyway, that's all I got. I think that tomorrow I'm going to start radiation heat transfer. If can we have a test again next week sometime? Which day is convenient? Anybody? Can you tell Krishna? Can you let me know? Is it Monday, Tuesday, Wednesday? Any of the days? It's fine.
Yes, sir, anything is fine.
Can you let me know?
Okay, so I'll ask around later.
Yeah, just ask them and then let me know. Okay, if there is no questions, then I'm dismissing you all, guys. Okay.
Thank you, sir.
Okay.